All right, I'm going to ask you guys as we go. I'm not writing this down, so hopefully you are writing with me. Here we go. Hallie, what's the color of phenolphthalein in an acidic pH? What's the color of phenolphthalein in an acidic pH? Double check yourself. I'm looking for PS19, so leave that at your desk for me while I'm walking around, okay? I'll come right back. Clear, good. So that's clear in an acidic pH. Jasmine, what is it in a basic pH? It is what? Pink. When it turns colors? pH 9-ish, yes, very good. What two flavors does the litmus paper come in, Graham?
Blue and red.
Blue and red. Anna, what color does the red one change in the presence of acid? Blue. Nope. Which one does it? What color does it change?
We'll go from blue to red.
Alright, so what color does the red one change in the presence of an acid? It doesn't change. Okay, so it's not tricky. It's just a thought-provoking question. And then, okay, so Anna, what color does the blue one change in the presence of an acid? Anna, your voice? No, Anna. Go ahead. Thank you. Okay. I'm doing one of answering concepts, so it's just a struggle here. All right. In terms of how to determine the pH of a weak acid, I do have to write this one down. This is number 13. Yes, 13 on problem set. You had to determine you had to look up how to determine the pH of a weak acid. What we've assumed so far is that every single time we have a strong acid, how does it dissociate? 100% dissociation. So if we had an acid, which we just generically call HA, and it makes H plus and A minus, we assume that whatever we had in terms of its molarity, we assumed that was the H plus, and so that made it quite easy. We were like, hey, yeah, pH is negative log of H plus. That was how we did strong, right? Now, this is all I'll expect that you will calculation-wise be able to do. But what you should be able to assume is that, hey, in weak stuff it doesn't do this, so can we calculate it the same way? No, because we'd have to know the percentage dissociated. So like if I had 1 molar and only 1% dissociated, super small amount, you're not going to have very much H plus to find the pH of. So you actually have to do something called an icebox, which is what we'll talk about we'll talk about right after break. So if the acid dissociates in a reversible fashion, which means the reversible arrow means that's a reversible reaction, which means that it does not go 100%. We are going to have a little bit of H and a little bit of the anion made. So let's say I had 1 molar of this acid. This is a weak acid, and not all 1 molar of that will dissociate. I'm only going to subtract or react a small amount, but because we don't know what that small amount is, we call that just X. Just X, that's it. So I'm going to subtract or react X amount. I'm going to make as I produce, so as I react on one side, I'm producing on the other side, right? Law of conservation of matter, as it reacts, it makes stuff. So I'm going to make, meaning add, X amount of H plus, and then the same thing for the 1-to-1 ratio here with A minus. So at the end of the reaction, I have 1.0 minus X. Kelsey with me? And then I have X and X. So this is something I'd have to do, and I have to do a little bit more math, but I cannot do pH is equal to negative log of H plus. I just cannot do that because that's not an appropriate way to solve for pH with a weak acid. So just kind of write there's a different route, and the math looks like this, but that's all I'm going to ask you to write right now. Okay? So just as a thought though, where do you think the pH would fall for a weak acid? Shout out a number. Closer than 7, but not 7. So like 4, 5, 6. So where would the pH of a strong acid fall? 0, 1, 2, 3, something like that. So 3 is kind of the breaking point. Could be below 0. Yeah. All right. So next couple questions here. I'm gonna leave those for you guys to chat with right now at your table.
Sour is acid.
All right, so back to me. Back to me. All right, describe a chemical reaction between an acid and a metal. Emma, give me something here. An acid and a metal, so make up one. Give me a metal. Give me a metal. Sodium. Okay, what acid do you want? HCl. Anybody? Hydrochloric acid. What kind of reaction is this? Thank you. And so as it single replaces, who gets with who, Emma? Diatomic? Okay, so H can't be by itself, it's a diatomic, so we'd have to go back and balance this out. Okay, so anytime you have a metal and an acid, it's going to do a single replacement reaction, and with the respect to that, what it looks like, what is it, how does it show you that a chemical reaction occurred? Okay, so we can see the chemical rearrangement, we can see it, new products are made. If you did this in the lab, what would it look like? What are we producing, guys?
Salt.
But you can't really tell it's salt. It's really just a white powder. But you could tell it was making what, Evan? Hydrogen gas. And how would you test for hydrogen gas? There was one test we did. So it's a flaming splint test, but when you hold the flaming splint up to the hydrogen gas, what happens? It bursts. Remember the boop? Do you remember that one? So it's called the hydrogen bark test. So we should know. That was with the types of reactions lab. We should know how the hydrogen bark test works. What happens when you put a flaming splint into carbon dioxide? Goes out, extinguishes, and then what happens when you put flaming splint in the presence of oxygen? It gets bigger because it will cause the flame to ignite. Okay, good. Now we have a characteristic list here. These are like multiple choice questions. You should be things like this you should expect to have on multiple choice tests. Okay, so given this data, which is an acid, Anthony's table. You guys are talking about this. Ready when you are?
Z.
Why Z? Okay, so
When you have a W,
so W says no, it doesn't taste sour. So how is that a dead giveaway? So bases are bitter and acids are sour. Slippery would indicate what? Acid or base? Base, right? Bases we know like soap is slippery. Litmus paper blue would indicate, if it did turn blue, it would indicate what? A base. Okay, so yes, yes, yes. The litmus paper I think is like the biggest dead giveaway. And then turns red litmus paper, or turns litmus paper red is the only one this is right here is the acid. Good job. Okay, based on the hydroxide ion concentration, which substances would be, oh my gosh, the board is off by like an inch, which would be an acid. So you have A, 1, 2B, 3C, 4D. Just hold it right here. Let me see. All right, you got like 5 seconds. have just a crazy number of numbers out there. Okay, so I got a lot of 1s and a lot of 4s. So which would be an acid? You guys tell me first. Is this a large or a small concentration? Relatively. No. That is large. That is 0.01 versus this, which is like 0.000001. That is a large concentration of hydroxide compared to all these. So is this acidic or basic? This is basic because we have a lot more hydroxide than we have hydronium, because remember that these numbers right here, when you multiply them together, they equal 14. So what is this, the hydronium concentration for A? So A, the hydronium concentration, you should be able to do this in your head. If the total is 1 times 10 to the negative 14, and this is only 1 times 10 to the negative 2, what do you complete that with? 12, right. So hydronium is 1 times 10 to the negative 12. That's like super small, right? Relative to that, that's quite large. This one's basic. So do the same. B, if that's the hydroxide, what's the hydronium? 1 times 10 to the negative 10th, because that's negative 4. Negative 10 plus negative 4 is a negative 14. So is this one acidic, basic, or neutral? Still basic, because that's quite large. This one? What's the hydronium?
1 times 10.
Good, so you're just making it 14, negative 8, negative 6, negative 14. So yeah, again, still basic, because we haven't met the point where hydronium's higher than hydroxide. The last one, what's the hydronium? Negative 6, which is bigger than negative 8. So this one right here is acidic. I had about maybe a third of you on part here, so you do have to think about the relationships. Okay, good so far. All right, so what we're going to do today is we're going to finish up our neutralization mix. So either have this in your foldable, your little booklet, or write these separately, because we were writing them separately at first. We're going to do neutralization, hydrolysis, which is just double replacement, double replacement, double replacement. Super easy. You just have to know the names of ions. And then we're going to do a titration. Okay, we're going to talk about titration. Oh, I'm still checking problem sets. Check your true false for a minute here. Still checking problem sets. You should be checking. Okay, let me scroll down a little bit for you. If you can't read this, 9 says not true, 10 says not true, 11 always true, 12 sometimes, 13 sometimes, 14 never, because 1 does deprotonate at a time, and then 15 sometimes. So what you should realize is that sometimes things are conceptually based, which is definitely like the true-false section, a lot more conceptual understanding, and then a lot of the free response on the bottom is mathematical. So I did look at 15. So 15 asks for the conjugates of phosphoric acid. So first of all, what is phosphoric acid? H3PO4. So this is an acid. The definition of acid in terms of Bronsted-Lowry is to do what? Drop an H, right? Donate an H+. So when you donate an H+ from a neutral overall no charge species, you're going to lose an H+, and you become not neutral, but anybody? Negative. So drop off 1, what do you get? PO4, 1 minus. Okay, that is 1 conjugate base. Do it again, because look how many H pluses it has left. Drop off another H+, what do you get? HPO4, 2 minus, and then drop off another one. No more H. PO4, what? Which is who? This is phosphate. So what you're seeing is that it's phosphate bonded to 3 separate H pluses to make phosphoric acid. We knew that was phosphate because that's how we named that particular acid. We see phosphate, we think phosphate, we change 8 to ic, we name it phosphoric acid. So that's a series of conjugate bases. 1, 2, 3. So we should have all of them, not just one of them. Okay? So otherwise, there's some pH calculations. More questions on yes, 19A? Like random things you had some mistakes on? Right. I can go over more with you at the end of class. Some of you guys probably need to look over your stuff because you did it probably over the weekend. All right, so we did this Friday. Thumbs up, you know where we are. Okay, this is just acid-base neutralization. Acids plus bases generally make what and what? Salts and water, right? So there are a couple different salts that we will make. We got to go over 3 of these. We didn't get to go over the 4th one. So let's do this one together. Guys, this board. Okay. Calcium hydroxide reacts with acetic acid. Take a minute to write down that reaction, the products, and then try to balance that out. All right, chant with me. CA. Like that. Parentheses, thank you. Reacts with H. I'm going to put a parentheses around that so it's clear, like ion, 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 ion. So you can see those 4 different ions. All right, and pick up from there. Calcium is the cation. It bonds with who? Acetate to make calcium acetate, which is what? Good. Okay, so we're crisscrossing those charges every single time. And then, how do we like to write water in this case? Right, the positive cation, the negative anion, HOH. And I need to balance that, right? So what do I need? No, I'm not. 2 acetates here, 1 acetate there. I know that for sure. 2 OHs, 1 OH. Where do I need a 2? In front of the acetic acid. So there's 2 acetates and there's 2 H's. So where do I balance this 2 H's out? 2 waters. And that makes 2 OHs and satisfies the 2 OHs. So, okay. Oh. Neutralization? Done. Does neutralization reaction mean that the reaction is always neutral at the end? No. Neutralization just means what plus what? No. Go back to where you wrote down neutralization. Okay, so, but the word neutralization does not mean it makes the reaction neutral overall. It just means that you have acid plus base because it's attempting to take a really acidic and a really basic thing to a place where it's pseudo-neutral. It does not mean pH 7. So that's what we're going to talk about now is why doesn't it make pH 7? And it's because we have to consider how the salt, like in this case, calcium acetate, we have to consider how the salt reacts with the water to make some sort of different pH system. So hydrolysis, write that down for me. So hydrolysis and neutralization, you guys were on the same page in your booklet, but you should realize they have a relationship and it's just one is the reverse of the other. And you've probably heard the word hydro, now in my class, I don't know how many times. When you think of hydro, what yes, you think of water, good. And if you think of lysis, what does lysis mean? Say again? It means to break, right? So hydro means water. And like think of wasn't it? It was photolysis or photolysis. In honors biology, you learned about photolysis, where it took the light takes the water and splits it apart in photosynthesis. Have you had Miss McGaha, Miss Austin? You know, she used to be Miss McGaha, so she got married. Snap. Yeah. So, but lysis means to break. Okay. Lysis means to break. So, if you have water and it's breaking, it has to be reacting. So water is breaking the salt apart, meaning it's reacting with that salt. So H plus gets with who? X minus, good. And Y plus gets with OH minus to make, again, an acid and a base. So the acid is the H in the front, the base is the OH in the back. Moving on? Yes? So in these questions, I won't say salt plus water. I'm going to say hydrolysis of sodium chloride, hydrolysis of calcium acetate, hydrolysis of lithium chloride. I won't say, hey, add water. You have to know that yourself. So take a minute and you have 4 examples. I want you to write down 4 reactions. If you need your polyatomic list, if you forgot things.
Something plus water, salt is not which is a base.
Oh my God. One more time.
I don't know.
All right, back with me in 3, 2, 1. I know you get the first one. We know that really you can't mess that one up because everything is a 1, 1, 1, 1, 1 charge. So crisscrossing makes it really easy to do that. Calcium phosphate, thumbs up. Ca3PO4 2. Your crisscrossing charges, yes, yes. Everything here is that. Everything here has to be crisscrossed. Everything, even water. 1 plus OH minus crisscrosses a 1. Name this acid. Phosphoric acid. So I took the I took the phosphate with a 3 negative charge and the H plus, and I put them together. I don't put PO4 and then H. I put H first and then PO4. Crisscross charges all the way. And then calcium with a 2 plus, and the OH with a 1 minus. Crisscross. I get the two on the outside. Balance this for me. Go for it, Zane.
We don't all put a 6 in front of the HOH.
Okay.
And then a 2 in front of the phosphoric acid, and then a 3 in front of the calcium hydroxide.
So that's 3 calciums, good. 6 hydroxides, 6 hydroxides, 6 H's, 6 H's, and 3 calciums, 3 calciums. Thank you. All right, lithium nitrate. Chant with me. Li. Li. NO3. That's a 1 and a 1 charge. Nothing changes here. I'm just going to put parentheses. Bless you. I'm just going to put parentheses so it makes it very, like, clear. Li is its own thing. Nitrate is its own thing. Add to what? HOH. All right, pick up from there, Zoe.
HNO3.
HNO3. Wonderful. And
then it's LiOH.
And all of these had a 1-1-1 charge, so it actually makes it kind of naturally bounce overall. Will, pick up from there. Next.
Next one. AlBr2.
Look at aluminum again. It's in group what?
AlBr3
Good. So aluminum's in group 3, crisscross charges. Keep going.
plus HOH.
Parentheses 3, yep.
Plus HBr.
Good. And then everybody balance. Three HOHs and good. Yeah. All right, so just remember the big deal here is crisscrossing charges, and I will only say some salt is hydrolyzed or it's undergoing hydrolysis. You have to understand that needs to add what as a reactant? Adding water. Okay, so the big idea though from this otherwise is that when we have a hydrolysis reaction occurring, it's just making salt water, right? It's just the salt going in the water making salt water. Salt means what? Say again? Salt is a generic term for what kind of compound? An ionic compound. So all of these are salt water. It's not a specific term. A lot of you guys think, oh, salt means sodium chloride. It doesn't. It means ionic solid. So I'm making salt water, salt water, salt water. What I want to do is be able to predict, is that salt water neutral, acidic, or basic? Okay, so here's how you can predict that. So if you want to predict if it's pH neutral, acidic, or basic, the way you do it is you look at the products. So your job is to assign each of these products and call them strong acid or weak acid, strong base or weak base. So let's do that right now for all of these. So you guys have these on your paper. So help me out as we go. For the first one, NaOH, everybody? First, is it an acid or is it a base or an acid? Because you see an OH, it's a base. Strong or weak? No guessing here. What are you referencing? You're referencing your list or what over here? The lowercase b. Yep, sodium's in the lowercase b. It is a strong base. So I'm going to put SB, strong base, under there. Okay, HCl. Strong acid because you've memorized your 6 strong acids. Okay, so we have a strong acid, we have a strong base. They're competing to make the pH what they want it to be. But do either of them win this pH battle? No, so it's strong and it's strong. They can't win on either side. So what is the pH? Neutral. That's how we determine if the overall hydrolysis process makes an acidic, basic, or neutral solution. Try that for the last three examples. Assign strong or weak. Decide if pH neutral, acidic, or basic. I need to see you writing SB, SA. So like this is the stronger weak acid. This is an acid H plus. H in the front means it's base. I mean it's an acid. That's an H in it. So is this one of the 6 strong acids? No, so it's weak acid. Okay. Is this is a base? Oh wait, right? Is this one of the stronger weak bases? Strong. CA. Okay. Oh, okay, I was right.
Oh, yeah. Well, I say strong base. Okay, so the fourth one next to
All right, come back to me. 3, 2, 1. Jacob, your table. Tell me, is this solution acidic, basic, or neutral?
Neutral.
The calcium phosphate.
Basic.
So everybody, thumbs up. Phosphoric acid is a weak acid. How do you know?
It's
Not on the 6 strong, right? And this is a strong base because it's in the lower B, so this is a basic solution. pH above 7. Everybody, next one. We saw nitric acid, lithium hydroxide. Both of those are strong, so overall neutral. And aluminum hydroxide is weak because it's not in the strong. It's not strong, but it's not in the lowercase b. And hydrobromic acid is strong, so this is acidic. Okay, this is on your PS 19B. So you can do this now on problem set 19B. Where we want to find PS 19B? On the lecture notes I provided for you, because you didn't even have to print it yourself. Okay, so it's on the same side of problem set. Okay. Last bit for the day is titrations. It all utilizes the same things we've been working with, from pH to stoichiometry to writing balanced chemical equations. We are doing a titration on Wednesday, like physically in the lab. So that's like my helicopter mom moment. I have to be like hovering over you because there's like $2,000 worth of equipment out, and it's like glassware. You know, you look at glass and your breaks, right? So what we'll do, and this is you guys good? Okay. So what we'll do is we'll use these things called burettes, and burettes with the flask and a combination of chemicals, we'll look for some color changes. In this one, it's turning pink. What indicator am I using? Phenolphthalein, right? So at the initial starting point, you can already tell this pH is what? Acidic, and over time, I'm adding what to this? Base, and as I'm adding the base, it turns pink. So what we have here is something called a burette. Okay, so the burette is this long thing with this thing called a stopcock. Go ahead. Okay. So as this stopcock is turned, it's going to dispense a small amount of base into this acid. Over time, as maybe the solution starts up high, and then we add some more, and then we add some more, and then we add some more. As we add this, it's getting more basic, because I'm adding base. So this is called a titration, and it's a volumetric analysis. So we're looking at the volumes of base dispensed, but we have to have like numbers, right? So these burettes, they have numbers on them. It starts off at like 50.00. No, actually lies. It starts off at 0.00. It starts off backwards and it goes down to 50.00 milliliters, and then we look to see how much we've dispensed. So we have to look at those numbers, and then we take the numbers and we compare them. We do some stoichiometry. We find the pH. That's what we're going to do now. Okay. But it requires an acid-base reaction, which is also termed a neutralization reaction. All right, so this is what you guys had started to draw on your booklet. Yes. Yes. Okay, you have this in your booklet. Yes or no? The last page. Okay, the last page. So I'm going to come right back to this. I'm actually going to sketch it with you. So if you don't have everything on your booklet yet, now's the time. Please write this part down here. So titrations are volumetric analysis. So we have to have volume. Titrations are volumetric analysis. So it's a method. It's a procedure. And with that volumetric analysis, we're using molar concentrations. And we're going to use those molar concentrations for a purpose. And that purpose is to find an unknown concentration. So one is a known concentration. So I'm going to say known molar concentration. And our job, our question, is to determine the unknown concentration, aka molarity. Concentration for us is molarity. So we have our axes. You guys probably wrote this down. What were your individual axes? The y-axis first. pH. pH of solution, so I'm just going to put pH. And what's the bottom axis? So it's just volume, right? Now, specifically, sometimes they'll say, I'm starting with an acid and I'm adding base. Or I'm starting with a base and I'm adding acid. So for this particular example, I'm saying that we're starting with acid and we're adding strong base. So I'm starting you off with acid. So I'm going to say volume of base added, just so it's clear, like I have the base in the burette and I'm adding this. So this is my burette. I have my little flask. There's acid in the flask and indicator. Sorry, this is over here in the corner of the board, but acid and indicator. So my favorite indicator, now you guys saw it 3 times now today. What was it? Phenolphthalein. Okay, so I have that in here, and in my burette, I have I'll have base. So we're going to drop that base. Okay. All right. So I'm starting off with an acid acidic pH. Where's that on the pH scale?
Low.
Low. Good. So I'm going to start off low, and I'm going to start with 0 volume of base added. So I'm going to start off down here like probably pH 1-ish. As I add base, what's going to happen to my acid? As I add base, what happens to my pH? It's going to increase, increase, increase. But is this a linear relationship between pH and H plus concentration? No, if it were linear, we'd have like a y equals mx plus b kind of mathematical calculation that we do every single time to solve for pH. But what do we do instead? What do I do to solve for pH from like an acid concentration? Log, right? So this has to have a logarithmic relationship. It looks like this. As you go, it's going to first kind of start off kind of level. I'm going to increase the pH a little bit at a time. And then all of a sudden, because of the logarithmic relationship, it increases exponentially. Okay? Exponentially increases. And I do have a certain like capacity for pH, which is what? 14. So then it's going to kind of level back off again. Okay? So it's supposed to kind of look like an S curve. So there's this logarithmic relationship. It's an exponential increase because as pH increases, or as a concentration of hydronium decreases, the pH jumps really high, which is what this is, and then it levels off. So what we have to know is there's like an anatomy composition of this curve we have to be familiar with. The halfway point between the vertical section, so like here's the vertical section about here, halfway between that is called the equivalence point. And we should know that when there's one true fact about the equivalence point, it's when moles of acid equals moles of base. So from that information, we can find out concentrations. If I have moles and I have moles, what else do I really need to get concentration? Liters. I need like a liter of a solution. I need some sort of volume. And where would I get volume in this type of experiment? From the flask, I might have some volume, and from the burette, right? So I have some graduations on there and I can measure it. Yeah.
So if a solution is on the equivalence point, would it be neutral?
It depends. So for this one, strong acid, strong base, they fight between acidic and basic, but where do they end? neutral, right? So this pH over here would be pH 7. But if it wasn't a strong acid, strong base, I would be wonky. I'd be one side or the other. But this is a strong, so I kind of don't, neither side wins. It is going to be neutral overall. That's why we just talked about that before. So that this one, equivalence point, pH is neutral at 7, moles of acid equals moles of base. Now, if I have a, let's say I'm using phenolphthalein, where does it change color? Approximately pH 9, like right here. So it's going to start to change color, like right there. What is that point called? It's not the equivalence point, but it's another point. There's another word for that. Say again? End point. It is called the end point when the indicator changes color. Okay, so that's a term. That's like a definition of your reading guide 19. So when I'm doing a titration, I don't see this curve. I'm just like titrating this flask. I'm like, okay, I'm waiting for it to change color. When it changes color, to me it says stop the titration. Hence the end point. I'm to the end of the titration. So the indicator is really important because otherwise I'm going to be titrating for days. That thing's going to stay clear. It's not going to change color until I put the indicator in there. Okay, so from this you've got we get a titration. We have some expensive equipment. We know it's an acid-base reaction. We know there's an equivalence point involved. We know there's an indicator involved, and values are attained from like this burette or the flask, like volumetric data. Okay. All right. So from all right, this thing is on the struggle bus today. Go ahead and answer that first together. What's the difference between the end point and equivalence point? Okay, so moving on. I just passed you a lecture note sheet, mainly because I have examples on there we're going to get to in a second. Alright, if there are extras, put them in the lab station for me, guys. Alright, shh, come back to me. Alright, so when we're talking about the stoichiometry, the math behind the scenes here, it's just normal stoich. It really is. But if we have too many quantities to choose from, sometimes we're not sure what to start with, so I've given you like a template on how to start. Remember at the very beginning I was like, we have a known concentration and our question is the unknown concentration. So if we have a known, we call that a couple of different things. We either call it a known, or we call it the titrant, which is going to be the thing in the burette, or we call it the standard. All of these things mean the exact same thing. It is the one I know everything about. I know both the molarity and I know the volume. So if I know the molarity and the volume, as you guys may remember, molarity, which is, what is molarity? Okay, I'm just going to put moles per liter for short. If I multiply moles per liter by liters, what do I get? Moles, because liters cancel and cancel, right? Okay, so once I get to moles, let's say, of the acid, and I want to get to moles of the base, how do I get from moles to moles? The ratio, the equation, what do you mean? The balanced chemical equation. Mole ratio, right, mole ratio, just trying to get that last word in there. So we're going to use the mole ratio to get to the moles of the other thing, which might be moles of base. But once we get there, sometimes we're like, what are we looking for? Are we looking for moles? Are we looking for grams? Are we looking for volume? Are we looking for molarity? It kind of depends on where we're going and that final step on how we're going to solve it. So you'll take your volume of your standard, which is your known, and you know the molarity and the volume of it. You'll multiply it by liters. You'll multiply by molarity to get to moles of the standard. This is on your paper someplace. And then you'll use the mole ratio to get the moles of the unknown, which might be base in this case. And you can do a variety of things. You can get from moles to grams. How would you get from moles to grams? Molar mass. You can get from moles to molarity by just dividing by volume, because moles divided by volume will give you molarity. there's a couple different things you can do. So I'm going to give you an example first. A student titrates 20 milliliters of a solution of hydrobromic acid. The titration requires 20.05 milliliters of a 0.1819 molar sodium hydroxide solution. What is the molarity of the HBr? So here's your thought process. You should always start the same way. Write the BCE. Go ahead and do that first. Okay. So write your BCE from this given. All right, Zane, get me started on this BCE.
We're gonna want to do NA, and then from C, OH,
Okay, so sodium hydroxide, he's pulling that from this as the reactant, and
plus HBr, which is hydro.
bromic acid, good. All right, Cole, pick up from there. Yeah, Cole. NABR, good, because that's sodium and bromine. Good. What kind of process is this again, guys? It is a double replacement, but specifically it's acid plus base, which is a what kind of reaction? Neutralization reaction. Neutralization. Okay. So I have this reactant and this reactant. All right, so we've done our BCE. Now we need to identify, like, who really do I know everything about? Who's my question? So the one that's called the titrant is the one that's truly the known. And the analyte, which is the one you're analyzing, you're looking at, like kind of deeply define some sort of question, that's your unknown. So like I said, there's a couple words, but they all mean the same thing. All right, so what do I know about the sodium hydroxide? From this question, what do I know? I know the molarity and I know the volume. I know everything about it. I know the molarity and the volume. So underneath that, I'm going to write down, oops. Underneath sodium hydroxide, I'm going to write 20.05 milliliters and 0.1819 molar. Just underneath it so I can see what I have. What else do I know, guys? Of the HBr, right? So 20.00 milliliters of the HBr. What do I not know about the HBr? And that's the question, right? What's the molarity of the HBr? So if it question molarity. All right, so now it's clear who do I have to start my stoic process with. Sodium hydroxide, right? It's the known. So if you need a helpful reminder, you can write titrant above sodium hydroxide and analyte. These are the fancy words, titrant and analyte. You could just put known and unknown, and that's going to be the same thing as these. So I have to start with these to do the math. Now molarity is what per what? Moles per liter. I'm in milliliters, so that's not going to match, right? So what do I need to do first? Okay, so convert that to liters. Ready when you are. How many liters is that? So how many decimals am I backing this up? There's 1,000 milliliters in a liter, so I'm technically backing that up 1, 2, 3. So 0.02005 liters of the solution. I'm going to multiply by what? I'm in liters. I'm good. Check. I've used that. Multiply by what?
Molarity.
The molarity. Right. You have this on your paper too to help as a guide. But you're trying to think, like, I don't really care about liters anymore. My job is to get from the moles of the sodium hydroxide to moles of the hydrobromic acid so I can then start to figure out stuff about hydrobromic acid. Because right now I'm stuck in sodium hydroxide until I get out of that. So if I multiply by molarity, what's on top? By 1819 moles of NaOH. You got to write the identity down. If not, Grant, you with me? Go stand up. If you don't write the identity, you won't be able to tell which is which. Cole, what's it on the bottom down here? No, that's only for gases. We're not dealing with gases. What is molarity, guys? One more time. Moles per 1 liter, right? Molarity, and we just reviewed that like last week. Molarity is moles per 1 liter. So this is 1 liter, and so this liter cancels. All right, so now I'm in moles of sodium hydroxide. Nobody cares about sodium hydroxide. What do I care about? No. I'm looking for HBr. This is my question. So where do I go next? The ratio. What's this ratio? 1 to 1. I know it's stupid. You're like, it doesn't change the number, but this is showing that you've moved from part A to part B. So from the given to the question. So 1 mole of what goes on bottom? NaOH. 1 mole HBr on top. Okay, we're so close. We've made it from liters to moles of sodium hydroxide, but that's going to cancel out moles of sodium hydroxide. Now I'm in moles of HBr. Remember, we're getting from molarity, and what's molarity one more time? Moles over liters. Now we have moles, right? I need to just get over liters, right? So let's just stop and calculate first. Calculate. Some at your table should have a calculator. Alright, so we got moles, right guys? Back to me. Alright, so once I get to moles, I want to get to molarity. What do I need to divide this by? Nope, I can't divide by 1 liter because that is not how much I had. Alright, so that is how many liters? 0.02 liters. So this right here is 0.02000 liters. So that's the liters that this was kind of taking place in of the HBr. So HBr moles divided by the volume of its own solution. And what do we get? 0.18235. And how many sig figs should we have, guys? 4. Good. All these up here have 4. So round this. 0.1824 molar HBr. What's up? So we took this, which is this right here.
Yeah. I know it's moles per liter, like since.
No, that's moles. This
They
one?
cancel out.
No, so this liter cancels and this moles of sodium hydroxide cancels, but this is moles of HBr on top. This is on top, so I'm leaving it on top. Yeah, yeah. Okay, so listen up, guys. All right, I'm about to move the desk back to lines. You ready? Go ahead and pack up. Pack up. Move your stuff back in lines. You got like a minute. Let's go. You're not helping me out here. Just move your stuff to the side and move the desk back. So much for collaboration. We'll try this again later. You guys will just move these desks like this way, like two blocks or something. So we have to move them. Alright, so I'm going to try to explain this again with your full and undivided attention. Not this same example. I'm going to do. Thank you. So what I wanted to say on here was that you can always do that reflection check at the end, because if you look up here and it's a 1-to-1 ratio and you used almost exactly the same volume, like 20.05 and then 20.00, those are almost exactly the same volume. You should realize that you're going to need almost exactly the same molarity because they're very close to each other in volume. They're a 1-to-1 ratio. You don't need but like 1 mole for 1 mole. So if we had basically that molarity, we're gonna have almost that same molarity. But since we need a little bit more sodium hydroxide, this is a little bit higher in concentration on the acid side. So that's how that balances out. There should be a correlation there. Do you see that? If it's a 1-to-1, it's almost the same molarity because they're almost the same volumes. We'll talk about that again. All right, so this next example gives you a little bit more of a scenario base. Do the same thing. You have your starting point. The word assayed just means tested, reacted, so don't worry about that. It just means tested. Guys, keep focusing. You're doing great. Continue. So you've written your BCE, you've written your given underneath the BCE. You're starting with your known for this week. Acetic acid. All right, everybody, what is your known? Who is your known? Sodium hydroxide, also known as your titrant, also known as your standard. There's 3 names, but they all mean the same thing. So how are you guys starting? Starting with which data point? Okay, so you're using these data points together, 22.70 milliliters, but I know I can't use milliliters, so instead I convert that to, so I'm putting what in the bottom here? 1,000 milliliters, and this is me not doing it in my head, just showing it out loud, in 1 liter of solution, okay? And then I've already used the liter, or the volume. What's the next one I use? The molarity, so that's 0.550 what? Moles of what? NaOH per 1 liter. So now we know molarity is moles per liter. Just as a reminder, it's 1 liter in this case. So now my milliliters can cancel. My liters of solution can cancel. I'm in moles of sodium hydroxide. Nobody cares about moles of sodium hydroxide. We care about getting to what? The molarity of the acetic acid. So what's next? Mole ratio. So what's on the bottom? 1 mole of NaOH. Top is 1 mole of acetic acid. Okay, so I'm going to show you, so we're solving molarity, which is the exact same problem from before. Last time I stopped here, right? I said find moles, and then we did what at the end?
And then you divide by the
Divided by the volume, right? Instead of stopping, I'm just going to show you another method. Jacob, you with me? So the same thing as stopping and dividing, you can also do it as just multiplying by the inverse. Do you know that's the same thing?
Yes.
Okay, so I'm just going to keep on going. This is multiplying by 1, so I'm inverting. What's the volume I need to divide by? So 15 milliliters, you're backing the decimal up to make it liters. So that's 0.015. So when I take the, oops, I never canceled. Moles of sodium hydroxide cancel with moles of sodium hydroxide. And then instead of just stopping dividing by moles, dividing by liters, I'm just taking the moles and multiplying it by the reciprocal, so which is 1 over liter. So what units remain? Moles of acetic acid over liters of the acetic acid solution, so that is molarity. So math, what's our answer? Point what?
832.
832 molar acetic acid. There we go. So it's just stoic. It's a reaction in stoic. It's actually no different than anything we've ever done. It's just the terminology, like analyte, titrant, equivalence point, titration. That's only really new stuff is the terminology. All right, so we're going to do another one, but we're going to solve for pH next. Okay? So look at 3 on yours. Do the same thing. Start with the same process. Yeah.
Let's try it.
No.
Want to hear that? Yeah.
Yeah, but you gotta know what to
Is it usually PS 19? Not with the I started it. I think I'm gonna have to make. And do you have your videos on this one? Yeah, I watched it.
Izzy, focus. All right, everybody should be approaching this exact same way, so you should be in the middle of your stoic someplace. You don't need me. I've done 2 examples for you, so keep going. All right, raise your hand if you have the molarity. Raise your hand if you have the molarity. All right, point what? Okay. 1, 2, 4, 6, 7, 9, but I'm going to round the 7 molarity. And this is describing the concentration or the molarity of what? Good. So make sure you write that down because then that will help you consider how to approach the pH. So once we get to our mole ratio, it was a 1 to 2 ratio, which is the only way that this is any different than any other problem we've done thus far. I want to find pH. So how do you guys want to attempt that, Aaron? Hold on. First of all, can we go straight to pH from a base? No. We have to go to what first? POH. So everybody, how would I, first of all, what is the equation to find pOH? Negative log of the hydroxide, right? All right, guys, what's the hydroxide concentration?
0.12.
Nope.
Oh, you divide by 2.
Nope. Which one is it, Will? You give me 3 options. Why?
Because there's 2 hydroxides.
Because for every single time this dissolves or dissociates, it makes what and what?
Strontium with 2 hydroxides.
So strontium 2 plus, right? That's SR2 plus what? 2, right? 2 OH minuses. So for this concentration, it's making double hydroxides. So it makes a 1 to 2 ratio in hydroxide. So what is the hydroxide concentration? No, that twice, right? So what is that times 2?
2.49.
Thanks. 3, 5, 9, something like that. So we have more hydroxide being produced than it had of itself because of the 1 to 2 ratio. For every one of these dissolves, I make 2 hydroxide, so I'm making double hydroxide. Okay, so that's going to be where we probably make a mistake, but now we know that, so I'll plug that into log, and what do we get? Hold on, sorry. So we get pH is what?
0.603.
Okay, so 0.6031. Does that make sense for a strong base for a POH?
Yes.
Yes, it's low on the POH scale. So this is POH, so then how do I get a pH? Good, so 14. So POH plus pH equals 14. Plug in 0.6031 here, plus X, right? You can solve for X, which is pH, equals 14. So when you subtract, you get pH to be what?
13.39.
And then we say, yay or nay, is that good for a strong base? Yeah, because that's really high on the pH scale. That is a good for a strong base.
Alright, that's not that bad.
Okay. So titrations. For our kind of complex setup, we are given data on molarity and volumes. We have some sort of combination where we know 3 things but not 1. We'll do 3 more examples on titrations tomorrow, so those lecture notes for the next 3. All right, we'll do that tomorrow. Right now, I'm giving you 10 minutes to work on PS 19B. Work. It was.
Oh yeah, I really, I have no help.
No, please. Please. Are you okay? No, it's okay. Are you okay? Are you sure? Alright guys, I can go ahead and do more examples, or you can work on the PS 19B. Let's go. Let's keep going. I'll keep you progress forward.